Alright, this is the Limpopo September trial exam question on the Doppler effect, question 6. And spoiler alert, this question has a simultaneous equation. Okay, when a sound source moves in an easterly direction towards a stationary learner. So now the learner is obviously listening. So we're going to say the velocity of the learner is 0. When the sound source moves in an easterly direction towards a stationary learner at 15 meters per second, that means the velocity of the source is 15. The frequency observed by the listener is F1. So the frequency observed by the listener is F1. Okay. Then it says to you, when the source is stationary, so now we've got the velocity of the source is 0, and the learner is moving towards the source at 25 meters per second, the frequency observed by the learner, which is the frequency of the listener, is going to be F2. The learner notes that F2 is greater than F1 by 37 hertz. So if F2 is bigger than F1 by 37 hertz, that means F2 equals F1 plus 37. Okay, so this is how we're going to set up our simultaneous equation. We have this situation, this situation over here is my first scenario, okay? And this situation over here is my second scenario, and we are going to link them with the knowledge of the difference between the two frequencies. So let's start answering the question. Write down the name of the phenomenon that the learner observes and state this phenomenon in words. So it is the Doppler effect, the apparent change in frequency or pitch of the sound detected by a listener because the sound source and the listener have different velocities relative to the medium of sound propagation. Then it says to you, for 6 marks, assuming that the speed of sound in air is 340 meters per second, so that is my V, calculate the frequency of the source. So we have to use our Doppler effect equation here, and we have to go, okay, let's go situation 1. We write out the formula. The frequency heard by the listener is equal to the velocity of the speed of the velocity of the sound over plus or minus the velocity of the listener over the velocity of the sound plus or minus the velocity of the source times the frequency of the source. Yes? So in the question they said to you the frequency of the listener in situation 1 is called F1. Okay? We know that the velocity of sound in air is 340, and in the first situation, remember we wrote it down from the question, the velocity of the listener is 0, and then we've got again here 340, and the velocity of the source is 15. So here is the question, what are we doing with this 15? We are going to subtract it because these two are moving towards each other. Okay, so if they are moving towards each other, we are going to get a higher pitch, so this fraction must be a larger number. So I get 340 over 325 times the frequency of the source. So you can cancel this down with your calculator. If you put this number in your calculator, you will end up with a fraction that is 68 over 65 frequency of the source. You can also turn this into a decimal, but you will have a much more inaccurate answer if you turn this into a decimal. So just leave this as a fraction for now. We've gone as far as we can with the first scenario. Okay, if we go back to the second scenario, we're going to do the same thing again in situation 2, and we're going to say the frequency heard by the listener is equal to the velocity plus or minus the velocity of the listener over the velocity plus or minus the velocity of the source times the frequency of the source. Except this time the question says, what is the listener here? It is frequency F2. The speed of sound in air is the same, 340. What is the velocity of the listener? It is 25. Now they are moving towards each other. In this question, the west and the east don't matter. It's the towards and away. So the direction of movement is immaterial. Is it towards or is it away? And then we are over 340 plus 0. So we end up with the second frequency being 365 over 340 frequency of the source. And if we simplify this, we will end up with 73 over 68 frequency of the source. Okay, now, like I said, do not put this into a decimal just yet, and you know your calculator likes fractions, so leave it as that fraction. And now we come back to what else it says to you in the question, that F2 is greater than F1 by 37 hertz. So we can come in here and we can just simply write 73 over 68 frequency of the source is equal to 68 over 65 frequency of the source plus 37. Okay, so now what do we have here? We just have like terms. So if we take the 68 over 65 over the equal sign, we get 73 over 68 frequency of the source minus 68 over 65 frequency of the source equals 37. And now, because we're basically in the last step of our calculation, now we can end up with our answer. So you just put this in your calculator, the coefficients in your calculator, 73 over 68 minus 68 over 65, and you end up with some number as a fraction. It's a random fraction, but it works out as to 0.027375 times the frequency of the source equals 37, which means that if you do your algebra, you will end up with the frequency of the source being 1351,57 hertz. So it's not a terrible simultaneous equation. Just remember to keep the fractions in your calculator. Now, it says to you, calculate the wavelength of the sound observed by the stationary listener. Now, if you're in possession of the original memo has got the wrong learner. I got the wrong wavelength here, because this question says for the stationary learner. So if the learner is stationary, we actually have to go back to this situation 1 with the stationary learner over here. Okay, and in this situation here, we know that F1 equals 68 over 65 frequency of the source. So what is actually the frequency heard by the stationary listener? It's going to be 68 over 65 times 1351,57 hertz, and this works out to be 1413,95 hertz. So because it says to you calculate the wavelength of the sound observed by the stationary listener, you first have to calculate what is the frequency of the sound heard by the stationary listener, and then you can go V equals F lambda. The velocity is 340, and this is 1413,95 hertz times lambda, and this gives you a lambda of 0.240461, which rounds off to 2 decimal places to 0.24 meters. Okay, now it says to you, write down one application of the phenomenon referred to in question 6.1 in the medical field. This is measuring the rate of blood flow in humans and animals, measuring the heartbeat of a fetus in the womb, which is an unborn baby, yes, and ultrasound scanning to look for different things. So now sometimes they say you're going to the hospital for a sonar, so I would be inclined to accept the word sonar, but in actual fact it's called an ultrasound. Okay, I think in the old days they used to call it a sonar, so if you're old like me you will call it a sonar, but in fact it is an ultrasound. Now, in question 6.5, if both the learner and the sound source are stationary, with what frequency will the learner observe the sound? So now the whole Doppler effect relies on the sound source and the listener having different velocities, okay? You only get the Doppler effect if the moving object travels towards you and away from you, or you travel towards and away from the sound source. If you are both stationary, you have no relative motion, so the frequency is exactly the same as the frequency of the source, okay? So what is the frequency of the source? 1351,57 hertz, okay? So you will hear exactly the same sound that the frequency of the source is making. You'll hear exactly the same frequency because you have got no relative motion. Remember, I always say that this is like if you're on the back of the motorbike, you hear do 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 with the motorbike, yes? But if you're standing on the side of the road and the motorbike comes towards you, it goes meow. You hear two different sounds, but the person on the back of the motorbike just hears do 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 because you are moving at the same speed. There is no relative velocity. So you will hear exactly the same frequency of sound.